Hello, and welcome to today's WJE webinar, Beyond the Routine Inspection. My name is Liz Pimper, and I'll be your moderator. During the next hour, structural engineers Jeremiah Fasl and Jeff West will discuss the in-depth and special field investigations and engineering analysis that are often required to answer critical asset management questions for maritime assets. This presentation is copyrighted by Wischan Elsner Associates. And now I will turn it over to Jeff to get us started. Jeff?
All right. Well, good afternoon, everyone, or good morning, depending on what time zone you're in. So as Liz mentioned, Jeremiah and I are going to talk with you today about doing inspections on maritime structures and primarily focusing on going beyond routine inspections and things that we do when we need to go beyond the routine. The learning objectives for the webinar are here. By the end of the presentation, you should be able to describe different inspection types for maritime assets, talk about the role that an inspection has in the asset management process for an infrastructure owner, identify several parameters that affect the corrosion service life of maritime assets, particularly those that are located in saltwater environments, and then finally summarize several techniques for performing a detailed assessment of a maritime asset. The outline is here. We're going to start off with a brief introduction discussing inspection of maritime structures, mainly introducing some terms and some concepts. We are going to talk a little bit about routine condition inspections, primarily where they fit in the asset management program for an infrastructure owner like a port. And then the bulk of the presentation will talk about going beyond the routine inspection. And in that, we're going to cover three subjects. The first is in-depth corrosion assessment and service life modeling. And then I'm going to hand the presentation over to Jeremiah, who's going to go through two case study examples of going beyond the routine, looking at a fatigue evaluation on a shiploader and then a wharf substructure evaluation. So the term maritime structures is a fairly broad term. These structures might also be referred to as waterfront facilities or shore facilities. And the types of structures that we're thinking about when we say maritime structures are quite numerous. Common ones would be wharves or piers or docks or bulkhead walls, marinas, and dolphins. Probably the most common one that we encounter is the wharf structure. This particular example here is at a container port. The wharf is outlined in the yellow dashed line. So it's oriented parallel to the shoreline, and the vessels or the ships are moored at the offshore face. We take a look at that structure from the water side. We see that the structure actually looks somewhat like a bridge that's essentially parallel to the shore. A pier is another common term. These are maritime structures that project from the shore, either perpendicular or at an angle, as in this case. And this allows vessels to moor on either side of the pier for cargo loading and unloading. This example of a pier here is actually two piers that are essentially perpendicular to the shoreline. And at the very bottom of the figure, we see a small craft harbor, marina, or dock. This is an example of a dock structure, in this case, a T-head dock, typically much smaller than a pier or a wharf and commonly used for locations where they're loading dry bulk material or liquid bulk material. In this case, it's liquid petroleum products going into a tanker. Because the dock structure itself is fairly small, it also is used along with other maritime structures like berthing dolphins and mooring dolphins to secure the vessel in place during loading or unloading. A bulkhead is another common maritime structure that we are often asked to inspect. They are essentially structures that retain earth fill along a waterfront. In this location here, the bulkhead retains fill and is not used for vessel berthing or mooring. Pardon me. This particular bulkhead is made of a common material, steel sheet piles, and has a concrete cap on it. So there are a number of reasons why we might want to perform an inspection on a maritime structure, and there are a number of good references out there for doing inspections of maritime structures or waterfront facilities. One of the primary references is the ASCE 130 document, Waterfront Facilities Inspection and Assessment. Some of the reasons why we might do an inspection, certainly the most common one, is that we need to know the current condition or estimate some future condition, primarily relating to asset management. An owner needs to decide what needs to be done and when with their structure. May also be a change in ownership or lease, so we'd like to establish what the condition is so that can be accounted for in the negotiations. The owner may choose to modify how they use the structure or increase the loading, so an inspection would be done to establish the condition at that time. And then, unfortunately, sometimes structures are faced with known or suspected problems, and an inspection needs to be done to characterize that. Most commonly, signs of deterioration, things like steel reinforcement corrosion in a concrete structure or corrosion of steel elements, wood decay if there are timber elements on the structure. Could also be geotechnical problems like settlement or erosion, vessel impacts, or if there's been a severe weather event like a hurricane. There are a number of different inspection types or terms that we use to describe those inspection types for maritime structures. Already using the term routine, certainly this is the most common form of inspection. It's typically regularly scheduled, and it's used to define the condition of an asset at a point in time. And if those inspections are done regularly over time, it enables us to track the conditions of the asset as it ages. A baseline inspection is another common term. It's essentially the first routine inspection that's done to establish initial condition, either for a new asset or for an existing asset where there isn't a good previous inspection record. Going beyond the routine, we get into what we refer to as in-depth or special investigations. And these are usually prompted when there is a problem and we need to determine the cause and severity of the damage or the deterioration, or even if a failure has occurred. They typically involve testing on site as well as material sampling, and frequently they involve an engineering analysis, either a strength evaluation to establish a load rating, or service life modeling if durability is in question. The outcome of that in-depth or special investigation is generally used to determine if repairs are needed and how urgent those repairs might be, as well as collect the information we need to do a repair design. So we need to understand what's causing the problem, how severe and widespread is it, and what are the quantities associated with that so that we can develop repair construction documents. Broadly speaking, the first two are the more routine inspections, and the approach that we use there is a more broad or general approach that can be applied to many structures in an asset inventory. The inspections are primarily visual, and the data that are collected are normally used for asset management decision process. In contrast, the in-depth or special inspection typically is focused on one structure that may be suffering from one or more problems. And in that sense, then the approach that's used is case specific to the structure and the known or suspected problems. And it's typically a much more involved investigation. So next, I want to talk briefly about routine condition inspections and primarily what their role is as part of an asset management system. And an asset management system for an infrastructure owner like a port authority is primarily a decision support system. And from a structural aspect, it's primarily there to answer questions like what's the current condition? Does it need repair? And if so, when? Should it be replaced instead of money spent on repairing it? And finally, is it okay if we do nothing, at least for now? So this decision support system is essentially there to prioritize capital expenditures, and it is a heavily data-driven process. And some of the data types that are used would be the asset operational performance requirements, the value of the asset and how much money is made from that maritime structure, what are its functional and structural characteristics, and then certainly the topic that we're covering today is what is the condition of that asset at present now, or what might it be in the future? So the objective of doing an inspection or a condition assessment for asset management purposes is really to get the input data that are needed for prioritizing capital expenditures. So this involves establishing that asset condition at some point in time, now or the future, monitoring ongoing deterioration or damage, identifying conditions that require maintenance or repair or replacement, and identifying conditions that might compromise facility operations. So even if there isn't a safety concern, there may be operational considerations that mean we can't use that asset in the short term, at least, which compromises revenue. Or we're also interested in identifying conditions that might lead to property or environmental damage. So the primary approach to collecting this input data is with a routine inspection program. And at WJE, we have considerable experience performing routine inspections. We also have experience working with port authorities to develop condition assessment programs. And our primary experience there is with Port Houston, where we collaborated with the port to develop the Maritime Facilities Inspection and Condition Assessment Program, or FICAP, or also known as FECAP. And this is an example of a condition assessment program that was specifically developed for asset management purposes. Our work with the port began in 2016, where we developed the FICAP Maritime Structures Manual and Program. And in 2020, we supplemented that working with the port in the form of the FICAP Corrosion Program, which is specifically aimed at establishing the condition in present and in the future of corrosion protection systems like coatings and cathodic protection systems on maritime structures. Some of the key features of those programs are that they use an element-based inspection approach based primarily in what's done for bridges, but tailored here towards maritime structures. Defines different inspection types, including routine, and it provides an overall asset condition rating, so conditions between assets in an inventory can be compared. Uses standardized data collection, standardized documentation, defines requirements for integrating that data that's collected with the port's database, so typically Microsoft SQL or a GIS system. Defines the qualifications for the inspection and condition assessment teams. And in general, it provides more specific requirements that are included in the ASCE 130 document. And the specificity primarily relates to gearing this towards asset management. I used the term standardized twice on the preceding slide. This is a very important part of doing a routine inspection, since ultimately the goal is wanting to get a comparison of asset condition between asset A and asset B and asset C. And that helps us with the prioritization then of capital expenditures for repairs or future replacement or modifications. Also, when we collect the data routinely over time, it allows us to evaluate system and material performance, really, and then it enables a value analysis. So some of the things we might do with that data would be to look at how well the money that's spent on corrosion protection measures like cathodic protection or coatings is being resulting in extended service life of the structure, or how long do replaceable systems like modular fenders and wearing surfaces last. But sometimes a routine inspection is not enough. In the upper right here, we have a steel dock structure that was hit by a vessel. In the lower right, we have a reinforced concrete structure that's experienced severe reinforcement corrosion. Since the routine inspection is typically visual, it's pretty good at giving an overall assessment of the current condition and identifying obvious conditions that might require repair, but it doesn't provide enough information in all cases. And that's when we need to go beyond the routine and perform a special or in-depth investigation. And typically here we're trying to answer questions like, is it safe? Can we keep using it? Or how long will it last before at least we need to do a major intervention or repair? And then finally, how do we fix it? And then the question that often gets overlooked is, how do we prevent this from happening again in the future? And the first scenario of going beyond routine that we're going to talk about is an in-depth corrosion assessment. And that in-depth corrosion assessment commonly has the objective of answering a question like, how long will it take for a structure that looks like this, which is in quite good condition, to look like this, which is suffering from fairly severe reinforcement corrosion? Or the companion question here would be, if our structure already looks like this, how do we fix it from a structural safety perspective and then extend the service life moving forward? So in order to do the in-depth corrosion investigation, we need to understand that fundamentally reinforced concrete corrosion is a time-dependent problem. And that's illustrated schematically here on this graph, where on the y-axis we have deterioration of a given element of that structure, and on the x-axis we have time. And the time is split into two main periods, an initiation time and a propagation time. And during that initiation period, or stage one, if our structure is in salt water, we have chlorides penetrating the concrete. And if it's exposed to the atmosphere, we have carbon dioxide that's carbonating the concrete. Eventually, the chloride levels or the depth of carbonation will reach the point where the steel begins to corrode, and we move into stage two of corrosion. Here we have internal damage occurring. The steel is corroding. The corrosion products that are developing have a larger volume than the original steel. So we get expansive internal stresses that cause cracks to radiate outward from the steel. At this period of time, corrosion can be happening, but there are no visible indications that corrosion is present or is ongoing. Eventually, the corrosion damage will get enough or severe enough such that the cracks erupt at the surface, and we get surface damage in stage three. And as it progresses further, typically we'll get delaminations, eventually spalling that exposes the steel, and we may experience severe steel section loss. So a common question that we are called upon to answer is, where are we on this time scale? And if we're in stage one or stage two, there may be no visual evidence that corrosion is happening, but we need to be able to characterize where we are. And in order to answer that question, we're going to ask the structure by performing an in-depth corrosion assessment. And typically that will involve a field investigation as well as a laboratory evaluation of the materials from the structure. So the in-depth corrosion investigation requires considerably more information to get a good understanding of current condition to assess corrosion risk or corrosion damage that's present. And typically that's going to involve a visual assessment, a delamination survey, which involves hammer sounding on the concrete or chain dragging on horizontal surfaces. And there we're listening for hollow sounds that would indicate we have an internal delamination that's developed because of the corrosion damage. Normally perform non-destructive testing and corrosion measurements, and will normally collect material samples for laboratory examination. Begins with a visual survey. We'll look at 100% of the structure, as well as perform a delamination survey on about 10% of the structure. So that's commonly the hammer sounding again to find hollow areas. And the purposes of the visual survey are to give us an overall indication of what's going on and how bad it might be, but as well it helps us choose representative areas for a more in-depth investigation. Normally we're using half-cell potentials, which are a non-destructive electrochemical technique. And the data gives us an indication of the corrosion risk, even in areas where there are no outward signs of corrosion damage. The half-cell potentials that we record can be plotted on contour maps, and this can indicate hotspots where we have a high probability of corrosion, even if there's no cracking or delaminations or spalling present. We also take corrosion rate measurements. These help us identify areas that are actively corroding at present. We can actually measure the corrosion rate or the amount of steel that's being lost over time. Typically, we'll supplement those half-cell potentials and corrosion rate measurements with concrete surface resistivity. This correlates with the risk of corrosion. And we'll normally do a reinforcement survey using ground penetrating radar, or GPR. And this helps us establish what is the as-constructed concrete cover to the steel, as well as identify the reinforcement locations and spacings. This technique uses a high-frequency radar antenna that transmits electromagnetic pulses into the concrete, and then we get reflections off embedded steel or other internal defects. We interpret those GPR signals to estimate what the concrete cover is, as well as reinforcement spacings and locations. After we've completed the non-destructive testing and the corrosion rate measurements or half-cell potential measurements, we switch into sampling roles. And for a concrete structure, we're primarily focusing on sampling concrete cores. Here we're going to sample cores from different elements in the structure, as well as different exposure conditions. This photograph here shows taking a core from a drilled shaft within the tidal zone at low tide. The second photograph here shows taking a core from the underside of the deck, which would be considered in the atmospheric zone of the structure. We're going to take those cores back to our laboratory and test them for strength, do chemical analysis to understand the chloride levels and the carbonation depth, and then perform a petrographic examination on selected cores. The petrographic examination gives us information on the composition and the quality of the concrete. And if we've got record documents like the original concrete submittals, we can even compare them to see if the as-constructed concrete matches those record documents. But what we're primarily interested in is understanding whether there are any concrete-specific deterioration mechanisms. So those could include alkali-silica reactions or sulfate attack from sulfates in the seawater, or if we're in cold environments, looking at the extent and severity of freezing and thawing damage to the concrete. We'll also perform testing to establish the chloride levels in the concrete of the cores. And here we're going to collect samples, powder samples out of the cores at increasing depths measured from the top surface of the core. And this gives us a chloride profile, or a concentration with depth through the thickness of the core, or at least the top portion of the core. We're going to do this for different elements, for cores extracted from different elements of the structure and in different exposure zones. And we're interested in the chloride levels because there's a very strong correlation between a chloride level in the concrete and risk of corrosion of reinforcement that's in the concrete. Once we've completed our field and laboratory investigation, we have the information we need to do service life modeling. And this lets us answer questions like, what is the remaining service life before some damage threshold is exceeded? And it also lets us evaluate the effectiveness of different repair materials or protection systems to extend service life. At WJE, we have our own in-house model for doing corrosion analysis. It's known as Fasl, which stands for Corrosion Assessment and Service Life Evaluation. It is a full probabilistic modeling approach that's based on concepts that are in the FIB model code for service life design. We're able to estimate the initiation and progression of corrosion damage using statistical inputs. And many of the inputs that we use in our model are defined from things that we measure in our field investigation and what we learn from the cores through our laboratory investigation. So we get a very structure-specific estimate of the remaining service life. The models will be performed for different exposure zones in the structures. This particular concrete wharf has primary elements, the drilled shafts, the deck, and then the drop panels between the drilled shafts and the deck. For the drilled shafts in particular, we're going to consider 4 different exposure zones: the submerged zone, a tidal zone, a splash zone, and the atmospheric zone. And we have different exposure conditions and therefore different risk of corrosion and potentially corrosion rates in the different exposure zones of these concrete elements. The inputs that we consider would be the age of the structure, and then primarily the concrete properties. And we need to recognize that these can vary significantly. So we're actually going to model the concrete properties statistically. And primarily here, we're talking about the concrete cover to the reinforcement, the carbonation levels, and then the chloride profiles. And those are using data that we've obtained from our in-depth assessment. And we'll actually establish statistical distributions for the concrete cover, carbonation depth, and for chloride profiles. Also take into account the exposure conditions by element type and exposure zone. So again, thinking primarily of tidal, splash, and atmospheric zones. And we can account for different design parameters, things like the properties of the concretes that are there for the original materials, as well as repair concretes, increased concrete cover if we're considering that as a repair, different reinforcement types, and then finally, if we're implementing cathodic protection or protective coatings. The primary output from our service life model is a prediction of damage over time. And here on this slide, this is illustrated on the y-axis as the percent of elements with damage, and on the x-axis, the age of those elements since initial construction. This analysis here was performed for a structure that was 38 years old. So the lines you see there, the blue lines are for elements that are in the tidal zone, the green for the splash zone, and the orange for the atmospheric zone. In this particular analysis, then, if we look forward into the future, when the structure gets to be 55 years old, the analysis would say that in the tidal zone, about 26 or 20%, 27% of the elements will have initiated corrosion, while about 20% of the elements will have reached some sort of damage threshold that we would determine working with our client. With the in-depth corrosion investigation and service life modeling, this lets us do improved decision-making about when should we implement repairs and what should those repairs entail. This graph here shows, again, on the y-axis, corrosion-related damage, and on the x-axis, the age of the structure since construction. And three curves are plotted. The solid dark blue line would be the do-nothing scenario if we just leave this structure alone. The orange dashed line would represent a repair strategy 1, while the blue dashed line represents repair strategy 2. In this case, if we do nothing, we would expect this structure to reach an end-of-life service criterion at an age of about 55 years. With repair strategy 1, we extend that to 65 years. And with repair strategy 2, that's implementing a cathodic protection system where it can extend the life beyond 75 years. So now I'm going to hand the presentation over to Jeremiah, who's going to take you through two more case studies of going beyond the routine.
All right, thank you, Jeff. As Jeff mentioned, I'm going to be talking about two project-specific case studies, one involving a fatigue evaluation of a shiploader, and then the other involving a vibration analysis, as well as some structural analysis of a wharf that was founded on timber piles. A shiploader is essentially a very large machine, and it's a very interesting machine. And although it's a machine, it has some structural aspects that the owner was concerned about. The shiploader is connected to a conveyor system where bulk material is conveyed into the shiploader, and then the shiploader distributes that material into the vessel on the left that you see. Here's a Google Earth image of the shiploader. The shiploader turns around a turntable pier and then moves along a radial track to access the various portions of the vessel that it's trying to load. And in the foreground, you can see the bulk material here, which happens to be petroleum coke. The shiploader consists of two main girders, and so this is very similar to a steel bridge. And it's supported on the left side by a turntable pier, and then the front supports where the radial track is located. On the top of the main girders, there's a shuttle and boom, and the shuttle and boom moves along rails that allow it to access different parts of the vessel. So the shuttle front wheels are supported on the top of the main girder, as you can see with the first arrow. And then on the back where the rear wheels are, it's supported on both the top of the main girder and the bottom, and that just provides some clamping resistance, overturning resistance as bulk material is moving along the shuttle and boom. Here we see the shuttle and boom in its fully retracted position, but in the next image, we can see that it's fully extended out. And so this is what the shuttle and boom can move out to load the vessel. And the yellow arrows just indicate where the shuttle and boom can move along the length of the shiploader. This movement causes stress ranges to develop in the steel girders and is one of the concerns that we'll talk about a little bit later. So the owner contacted us in early 2022, and they were in the process of replacing the rails. And when they removed the rails, they identified quite a bit of section loss underneath the rails. On a localized basis, the section loss was anywhere between 20 and 40%. And for a shiploader that's in a marine environment exposed to chlorides, it wasn't surprising that there was section loss. When you consider overall the width of the flanges, it corresponded to a reduction in their section modulus of 10 to 15% in the worst locations and less than 10% everywhere else. So they had some obvious questions of what are the possible consequences of this section loss. And the first is that the stress ranges are expected to increase from the observed section loss, and that may affect the long-term fatigue performance and safety of the shiploader. Traditionally, we would try and evaluate that long-term performance in a desktop study where we put the shiploader into an analysis model, we move the shuttle and boom around to see how the stress ranges vary. But unfortunately, they didn't know the weight of the shuttle and boom. They had good documentation on the main girders themselves of the plates, but they did not know anything about the shuttle and boom. In addition, they didn't know how often the shuttle and boom moved and extended out to load a given vessel. So we couldn't determine the effect of the section loss from just a typical desktop study. And so we proposed to install strain gauges on the shiploader at critical locations and then measure its response with time. So we installed strain gauges at locations that were critical, both from a fatigue detail perspective, as well as critical locations where the cross-section geometry is changing. We then measure the response for 3.5, 4 months to get multiple vessel loading events. And that way we can see how much variation from one loading event to the next there was. And then we could need to estimate how many loading events occurred prior to our instrumentation, as well as projecting into the future. And once we had that information, we could then evaluate the fatigue life. And we use the AASHTO manual for bridge evaluation to do that. This shiploader is very similar to a bridge, and so we can use a lot of the AASHTO provisions for evaluating fatigue life. By installing strain gauges directly and accounting for the locations of fatigue-sensitive details, we could understand the effects of the corrosion section loss on its fatigue evaluation. We had to determine the critical strain gauge locations. To do that, we assumed a generic weight of the shuttle and boom, and we moved it in a model to understand how it might affect the performance. From that model, we could identify that strain gauge locations 2 and 3 were the critical locations, and we'll show those here in the next slide. But we also installed gauges at strain gauge 1, which is just adjacent to the cantilever span, and then at strain gauge 4, where it's in the middle of the main span. At each gauge location, we installed 2 gauges top flange and 2 gauges bottom flange, and then we installed it on each of the 2 girders. So at each location, there's 8 gauges being installed for a total of 32. Here we're looking at strain gauge location 2 on the right, strain gauge location 3 on the left, and these were critical locations because they're adjacent to flange transitions. The strain gauge locations are the black rectangles that are on the girders just to the right of the transition regions. And they are where the stress ranges are expected to be higher, right adjacent to those splice locations. Now this is looking along the length of one of the main girders. Strain gauge location 4 is at the bottom, and then it goes 3, 2, 1, and then to the yellow arrow is where the data acquisition system was located. These strain gauges were installed adjacent to fatigue sensitive details. And the one that we were most concerned about were the connection plates from the braces being connected into the top and bottom flanges of the main girders. And in this first boxed orange area, you can see the orange arrow pointing to a connection that shows a 90-degree angle between the connection plate and the main girder. And that just makes it a lower fatigue detail than one that has a gradual transition. We collected stress history data from all the vessel loading events during our period. This one on the left shows a typical stress history. you can see that when the vessel first arrives, there's an increase in the stress to about 20, 25 KSI, and then it reverses back to zero and stays relatively dormant for a day and a half, and then you see a lot more activity occurring. And so there might have been an initial movement of the shuttle and boom, and then it stopped for a day and a half, maybe over the weekend, and then started up again. We then take that stress history and convert it into a histogram. The figure on the right is just showing the results of that histogram using a cycle counting algorithm. And it just shows you how many cycles occurred between 10 and 15, 15 and 20, and so forth. And with that data, we can then estimate the remaining fatigue life. And this is a graphical representation of that fatigue life. The shiploader was put in service in 1986. We're looking at sensor location 3, which had the highest stress ranges that were measured during our instrumentation. And when we evaluated this particular structure in 2022, you can see that the solid lines, which are the bottom gauges, as well as the dashed lines, which are the top gauges, they are below that minimum life threshold that corresponds to a 2% probability of failure. And so for these gauge locations, we haven't reached that threshold yet. And even if we project into the future, 10, 15 years is when the bottom gauges start hitting that threshold, and the top gauges takes even longer to hit that threshold. So from this data, we can conclude that we have a very low risk of fatigue cracks at present. We haven't reached that minimum life threshold yet, and that there is no immediate concern for fatigue damage. And it gives the owner a lot of understanding that it will take even 10 to 15 years before we meet that minimum life threshold. They can also manage how they evaluate risk long-term. They could inspect these connections at a regular interval. You could do it every 5 to 10 years, for instance, or you could do it based off number of loading vessel events that occur. Because this detail that we're concerned about is in the brace connections, they can actually repair those pretty readily if they identify them during an inspection. Alternatively, if they don't want to have to worry about doing inspections on a regular interval, they could preemptively try and repair this by either changing the fatigue performance, maybe adding a gradual transition between the connection plate and the flanges, adding cover plates, or a combination of either. And so this case study allowed them to understand their priority of when they might need to replace the shiploader or what type of maintenance activities are needed for the future. The next project I want to talk about is a liquid bulk wharf that was founded on timber piles. So this structure was built in the 1920s. It's 500 feet long and 50 feet wide. It has a timber substructure that was important and we'll talk about, and then a concrete superstructure built on top of it. It is used for liquid bulk activities, and so it has a shed on top and limited accessibility, about 20 feet, and limited light loads as well. They hadn't performed a routine inspection in quite a long time, and so they were asking us to perform that assessment as well as evaluate what happens if they deepen the channel adjacent to this wharf. This is just a typical view of the vent structure. It shows on the bottom that the platform slab and timber piles were built in the 1920s. The superstructure above that platform slab was demoed in the 1940s and then replaced with the current system, which is a shear wall system with spandrel beams, deck beams, and a deck. The supported structure that we looked at is highlighted in yellow. It's the yellow rectangle. We can also see the blue shed that overlaps onto the supported structure. There is a retaining wall that was original 1920s retaining wall, timber retaining wall that's still active. And then on either side, they've abandoned those timber retaining walls and replaced them with newer sheet pile retaining walls. The history of the dredge depth has varied for this particular wharf. In the 1960s, it was approximately 30 feet deep. They deepened it to 37 feet in 1988, and then wanted to deepen it further to 38 feet, plus have an allowance for an over dredge depth in 2014. As you can see, with each increase in the dredge depth, the pile depths that are going from bottom of wharf to the top of the soil is increasing. And that has an effect on the load carrying capacity of the structure. We did perform a condition assessment of the superstructure. The upper right-hand picture is the front of the wharf. And you can see that there's some trapezoidal rubber elements that act as fender elements. Some of them have even torn off, but you can see they're not providing a lot of protection because you see quite a bit of impact damage that's occurring in addition to corrosion as well. As you go interior from the front of the wharf, that's the bottom picture, you see that there's not a lot happening. There's not many cracks or delaminations that were noted. But as you go to the side of the wharf, which is the left picture, you can see there's quite a bit of retaining wall deterioration. There's full section loss through those steel elements. And there are concerns related to the slope stability of the structure. So we did do a service life analysis for this particular structure on that approach that Jeff talked about of doing in-depth assessment, performing the laboratory investigation and evaluating the laboratory results. The deck elements and typical deck beam elements that are well above the water, you can see that they have quite a bit of life remaining, and that's consistent with the observations that we had from the visual assessment. The shear walls, even though they appeared in pretty sound condition, they had quite a bit of chlorides that are embedded in those walls. And so we estimated that the remaining life was less than 25 years. A lot of the other front-facing elements are near their end of their life and need to be replaced just due to the amount of damage that they have. And then the piece I want to talk about next is the piles. The piles are spaced anywhere between 2.5 to 4 feet on center for the full width of the wharf. And so that corresponds to about 4,000 piles underneath this dock. If you can imagine trying to do an underwater inspection, getting into the interior of the wharf is not going to be very safe. And so we only had the exterior, the perimeter piles inspected and sounded. When the divers came up, they noted that the circumference of the piles could be penetrated with an awl, anywhere from 1 inch towards the top of the piles to 1/2 inch about mid-height. One of the battered piles was not connected to a shear wall, and then portions of the pile could be peeled away, as you can see in this bottom right-hand picture. And obviously the question is, what's the impact of the pile deterioration? Normally, we'd want to do more in-depth assessment of the interior piles to assess their integrity, but because of the safety concerns, we couldn't do that. So we proposed instrumenting the wharf with multiple geophones, accelerometers, so that we could understand the vibrational response of the wharf. After the sensors are in place, we impact it with a barge and then measure their response to the free vibration response. So this would normally be called an impulse response, just done on a much larger scale. The upper graph is just showing the vibrational response of the structure with the impacts noted at about 250, 1700 seconds on this graph. And then below that is the time frequency response. And you can note that there's a lot of activity happening in that 1 to 5 hertz range. And that just corresponds to the primary modes of vibrational modes of the wharf. We then developed a 3-dimensional computer model that incorporated all 4,000 piles. And because of their depth in the soil and the clay soil that we were investigating, we had to include a soil structure interaction. And from there, we could then extract out the primary natural frequencies of the wharf. We then wanted to compare this computer model to what we measured in the field. And we had to make some adjustments to our computer model. We had to soften how the piles were connected at the wharf interface to the superstructure. And then we had to reduce the flexural stiffness of those piles by about 50%. And when we made those adjustments, we got good agreement between the computer model and the measured data that we collected. And now with the calibrated model, we can then start answering questions related to load carrying capacity. We also evaluated the slope stability of this particular wharf. Prior to the dredging, the factors of safety were 2.1 for short term and 1.2 for long term. And then after the proposed dredging, we saw reductions in those factors of safety. For short term, post dredging, the factor of safety is still above what we would want to evaluate. For long term, we're seeing values very close to 1. And so the system's not adequate for those long term slope stability concerns. We did evaluate the load carrying capacity, and using the elastic model, it would tell you that the front line of piles are overstressed due to their increased distance, as well as the reduced flexural stiffness of those piles. But we thought that the shear walls are stiff enough to help redistribute load back to the shallower piles. And so we thought that the system was okay for gravity loads for now. But ultimately, the lateral system wasn't adequate. We had large soil pressures. We had concerns about that timber retaining wall. And then even deepening the dredge depth, we expect larger ships to be mooring, and we expect larger mooring loads to be affecting that. And as we mentioned earlier, we had a non-functional fender system. So the owner wanted us to come up with repair recommendations. They noted that this was a highly utilized wharf. And so we had to consider how to keep the wharf open for as long as possible while evaluating lateral gravity loads as well as the slope stability concerns. We proposed to drill through the existing deck and install new drill piers. Those drill piers could be installed long enough to extend through the slope line to satisfy slope stability concerns, and then steel plates could be installed over them to cover the holes. After all the drilled shafts are installed, we could then demo out the existing shear walls and the existing deck so that a new bent cap could be installed and a new flat plate slab on top of that in a sequential pattern. All of that is to accommodates the lateral loads that are necessary for this structure while giving them options to keep it open. So as we close up, I want to reiterate a couple points that Jeff made earlier. The first is that routine inspection is a critical part of our asset management program for marine structures. There's a variety of procedures out there of how to do that, whether it be ASC 130 or port-specific plans that for instance, the Port of Houston one that we helped develop. Those routine inspections provide critical data for the asset management program. They're generally visual, and so they give you an indication of current condition, and they can help you prioritize from one asset to another. And while they are useful, they do have limitations in predicting the remaining service life. And predicting remaining service life is a key part of expenditure uses of asset management. And that's where we often need to go beyond the routine to answer, is the structure safe in its current condition? Can it be left as is, and if so, for how long? And we provided multiple examples of doing in-depth or special field investigations or combined with engineering analyses, whether that was a corrosion assessment, a fatigue assessment, instrumenting the shiploader, instrumenting the wharf, or dynamic testing. We're essentially asking the structure the current condition and then using those engineering analysis to evaluate it for its remaining service life. And with that, I will pass it back off to Liz.
All right, thanks, Jeff, and thanks, Jeremiah. That was a great presentation. All right, let's take our first question. Why have you decided a minimum 10% for the delamination survey and hammer sounding?
I can take that one. So that is always a judgment call. There are some guidelines in some of the ASCE documents, particularly I believe in the ASCE 101 document for underwater inspections that talks about a level 2 survey involving at least 10%. So that's taken as a rule of thumb, both in the marine world and in other inspections of infrastructure type assets. And it's really intended to give a baseline indication beyond just visual. And while we're in the process of doing that, if we start to find that delaminations are quite prevalent, maybe in particular elements, then we will change our plan and likely increase how much we're doing. but no real basis. It's not defined by statistics or anything. It's just more of a rule of thumb.
Okay, our next question. What frequency of core sampling do you normally consider appropriate and why?
Yeah, another great question and somewhat related to the first. So generally what we will do is identify areas for in-depth study. And that's going to vary from structure to structure and what the expected deterioration might be or even what the expected mechanisms of deterioration might be. So nominally, we might try to do in-depth investigations in about 10% of the structure. On an element basis, then we'll go in and decide how many exposure zones does that particular element have and try to get representative cores from each exposure zone so that we can understand chloride levels if it's in a saltwater environment, and then a limited number of additional cores for strength testing and petrography. So the actual number of cores is going to vary quite a bit from structure to structure, but we're nominally targeting about 10% of the structure as in-depth study areas, and then deciding on how many cores we want in each of those areas.
Okay, a little more general question here. What are typical differences in saltwater versus freshwater structures?
I can take that one as well. The reinforcement corrosion in a chloride environment, whether the chlorides are from seawater or from de-icing salts on a bridge deck or parking garage, are generally about as bad as it gets for corrosion of reinforcement. So in a saltwater environment on the coast, we expect typically more severe corrosion. In a freshwater structure, the primary mechanism for corrosion is then carbonation. So exposure to atmospheric carbon dioxide, which takes generally longer to initiate, and corrosion rates tend to be a little bit slower than chloride-based corrosion. Normally, freshwater structures that have corrosion problems have low concrete cover from original construction, and then are the older structures, the ones that get up into multiple decades old.
All right, Jeremiah, here's a question for you about the shiploader. Was the predicted fatigue life based on stress cycle number, mean stress range, and the corrosion rate prediction?
It was based off of the stress cycle number. We incorporated the corrosion aspect in that we were measuring the stress ranges with the current section loss. We had recommended to them to maintain their coating system in the future so that they wouldn't get additional section loss. But it was primarily based off stress cycle number. And because we use the AASHTO fatigue protocol, mean stress range has no impact on that fatigue damage.
Okay, here is a follow-up question about the shiploader. How was the acceptable failure probability of 2% determined for the shiploader?
And that one's a similar answer in that it's because we were following the AASHTO manual for bridge evaluation. They have certain criteria, and their minimum life threshold that they have in that procedure is based off a 2% probability of failure. That's what most fatigue life damages, or fatigue designs rather, are based off of. And they allow, and because it's only 2% probability of a crack forming, they recognize that you can calculate the mean fatigue life, and they have procedures for doing that as well.
Okay. Our next question, can GPR results find for corrosion? I've seen it used for mapping the reinforcement locations, but not for corrosion. If so, is it accurate enough to map out a percentage of corrosion, or is it more qualitative?
I can take that one. So GPR is generally not a tool to use to find corrosion damage. So GPR is not even a great tool to determine bar size to begin with. So certainly it could tell you the difference between a number 3 bar and a number 18 bar, but most of the time it's just not the signal interpretation is not precise enough to distinguish bar size, so it's really hard to pick up if you had corrosion-induced section loss. So that's where we're pairing the GPR that's going to give us the concrete cover and the bar locations with corrosion assessment techniques of half cell potentials and corrosion rate, and then more generally the concrete resistivity.
Okay. On your chart, I'm not sure which one they're referring to, but on your chart, you show the propagation time as being linear. Is it linear or is it exponential in nature?
So since the word there is propagation time, I think this is probably the service life prediction or the representation of corrosion over time. We also had the fatigue life prediction as a linear estimate as well. So I'll answer the first part on the corrosion piece. So that first chart that I showed is highly idealized or schematic that shows propagation time as linear. The other plots that I showed later on were actual output from our service life model. And once corrosion initiates, those particular curves show it as not too far off of being linear. But there are factors that come into play that might affect the rate to make it nonlinear. So it's generally not necessarily linear. Not necessarily exponential. Once you start to lose the concrete cover, then corrosion rates will speed up significantly and the model predictions kind of go out the window anyway.
Yeah, and if I add on from the fatigue perspective, it all depends on the accumulation of future vessel loading events. If this was a bridge, they generally expect that you're going to get an increase in the volume of vehicles on an annual percentage. And so from that perspective, it can be exponential for fatigue accumulation. For our shiploader, the port that we were working with had about 15 years of data, and it showed relatively constant use of the shiploader. And so we just projected out linearly as well for the future. But that's something that they could modify their inspection protocol for nonlinear type vessel loadings in the future.
Okay. Do you use divers or ROV for any of the underwater inspections, especially at investigation phase of the structure's assessment?
Yeah, to date, we've used primarily divers, and WJE doesn't have divers, so we partner with other consulting firms to do those inspections. I think that we're interested in ROVs. We just personally haven't used them much.
Okay, we've got time for one more question. What is the criteria to determine the damage percentage for end of service life?
That's a great question. And that is one that we approach working with our client. So certainly from a structural perspective, we can go through an analysis to determine for an individual element how much, say, corrosion-induced section loss you could tolerate before the structure becomes inadequate from a strength perspective. But there are other things that often kick in even before it gets to that very severe or end-of-life criterion, which are the extent of visible damage, which is really going to be an owner judgment call in terms of what they'd be willing to tolerate. And then there are kind of rules of thumb related to, once damage gets beyond a certain percentage or certain number of elements have damage, then repair costs start to go up very fast. And so we generally want to intervene before damage gets, in terms of number of elements, gets to be extremely widespread. So normally we will have a conversation with the client and talk through some of these ideas and leave it to their judgment, really, in terms of what would the criteria be to define end of life in a service life model.
Okay. Thank you, Jeff. And thanks, Jeremiah. As I said before, that was a great presentation, lots of good questions. Thank you all for joining us. We hope it's been educational. So again, thank you so much for your time, and we hope you have a great rest of the day.